Today we're going to talk about Thomas Fermi theory. This is a forerunner of density functional theory, which was developed as early as 1927, so not long after the inception of quantum mechanics, and it gives useful insights into how DFT can be developed. So in the previous videos and lectures we discussed the uniform electron gas, which gave us some interesting insights and proves to be very useful in the development of density functional theory. But it's clear that it's not much use for the modelling of materials. We need to adapt it to a varying potential, which we're going to write V of R. And in materials and molecules, of course, this potential is given by the nuclear electrostatic fields. So the question is, if an electron gas experiences the field V of R, in other words, a position-dependent potential, what is the resulting density, rho of R? So we're going to start in this video with a simple example just to motivate our thoughts in future videos. So let's start by considering a non-interacting uniform electron gas in a box. And what we're going to do is we're going to divide the box in half, and there are going to be two potentials in the different halves of the boxes. So we're going to have a left half with a potential VL and the right half with potential VR. Now, naturally, electrons will flow from the area of high potential to the low potential, and so there will inevitably be different densities in the two halves of the box. Notice at this point that, of course, rho L and rho R will be uniform within the respective halves of the boxes, though they will be different. In a normal uniform electron gas, the highest occupied state, or the Fermi level, epsilon F, is given by h bar squared into 3 pi squared rho to the 2/3 over 2m. We saw that in a previous lecture. But given an external potential, this shifts to the chemical potential mu, which is just epsilon F plus V. So that's when we have a potential applied. In equilibrium, mu must be the same throughout the box. So in our simple box that I've got drawn at the top of the screen, we will have to have the same mu throughout. So we can write the following: mu L, which is just given by VL plus h bar squared over 2m into 3 pi squared rho L to the 2/3 must equal mu right, which is given by V right plus h bar squared over 2m into 3 pi squared rho right to the 2/3. Now, in general, we could take this example and we could decide to generalize it, but let's just look at the form of those two equations. What we're saying is that in this simple example, the density varies with position such that the following is true. Mu, which is the overall chemical potential, is given by V of R, the position-dependent potential, plus h bar squared over 2m into 3 pi squared rho of R. Now, we've not given a formal justification for this, but it's what we can draw from that little piece of very simple maths that we've done just above. And what we're going to go on to do in the next videos is to look at how we can generalize to a non-uniform field for the non-interacting electron gas, and then we will add back in interactions. We should note that Thomas Fermi theory is actually very crude and simple. It's not often widely used. It has given us some useful insights into density functional theory, and it does form part of an approach called orbital free density functional theory, which is more advanced than there is time for in these lectures.